Hello everyone, welcome back to our operating systems lecture series. In this session, we are going to discuss an important topic from Unit 2, Process Management. The topic is Inter-Process Communication, or simply IPC. Now the question is, why do processes need to communicate with each other? In the modern operating system, many processes may be running at the same time. Sometimes one process needs information from another process. Sometimes two processes need to share data, and sometimes processes needs to coordinate their activities. So the operating system provides mechanisms that allow processes to communicate with each other. This is called inter-process communication. Throughout this lecture, we will understand IPC with simple examples and diagrams. Let us begin. Before defining IPC in detail, let us look at a practical example. Consider the Google Chrome browser. Older web browsers were often designed using a single process model. In such a model, if one website creates a series problems, the entire browser may hang or crash. Chrome uses a multi-process architecture. That means different tasks can be handled by different processes. There are different types of processes. The browser process manages the user interface and important disk and network operations. Then we have the renderer process. The renderer process is responsible for rendering web pages and handling technologies such as HTML and JavaScript. A separate renderer process can be created for each website. This also provides an important security advantage. The renderer process can run in a sandbox. So it access to resources such as the disk and network can be restricted. There can also be separate processes for different type of plugins. So Chrome is a good practical example of why operating system need to manage multiple processes. And when these processes needs to exchange information, we need inter-process communication. Now let us understand the basic concept of inter-process communication. As we discussed in the previous slide, modern operating system run many processes simultaneously. These processes made to communicate with each other, to exchange information, to share data, and to communicate their activities. This communication between processes is called inter-process communication. Now there are mainly two methods of IPC that we are going to study in this section. The first one is shared memory system. The second method is message passing system. These two methods are very important in operating system. Now we will look at some practical example of IPC systems. So in this session, our learning path is very simple. We will understand what is IPC. Next, we will study the two major methods, shared memory and message passing, and then we will understand their working through examples and diagrams. Let us first start with the first method, shared memory. What is IPC? Let us define IPC. Inter-process communication refers to the mechanisms and techniques that allow processes to communicate with one another. Suppose we have two processes, process A and process B. If a process A needs to send some information to process B, there must be some communication mechanism between them. So IPC provides this mechanism. Why IPC is necessary? Because modern operating systems execute many processes simultaneously. These processes may need to share data, synchronize their actions, and or notify each other about events. For example, consider a web server. Web server may receive many clients' requests. Each request may be handled by a separate worker process. These worker processes may need to communicate with the main server process. They may share information about login. They may access common resources such as database, and they may need to coordinate different tasks. Therefore, IPC become very important. Why do processes cooperate? Now let us understand why processes are allowed to cooperate. There are several important reasons. The first reason is information sharing. For example, two processes may need to access information stored in a shared file. The second reason is computation speed up. A large task can be divided into smaller tasks, subtasks. These subtasks can be executed in parallel using multiple processes. This can improve performance. The third reason is modularity. A large systems can be divided into separate processes or threads. Each process can perform a specific function. A fourth reason is convenience. As users, we may edit a document, listen to music, and compile a program at the same time. Different processes can handle their activities. Now, there are two types of processes that we should remember. An independent process cannot affect and is not affected by other processes. For example, a text editor and a calculator application may operate independently. A cooperating process, on the other hand, can affect or be affected by other processes. Example, processes in a client-server architecture. To support cooperative processes, operating system mainly provide two IPC model. They are shared memory and message passing. We will study both in detail. Let us first discuss shared memory system. Shared memory is a memory region that can be accessed by multiple processes for communication. Normally, the operating system protects the memory of one process from another process. This is important for protection and security. But in shared memory IPC, two or more processes agree to use a common region of memory. This region is called shared memory region. The processes communicates by reading data from this shared area and writing data into it. For example, process A can write some information into shared memory. Process B can read that information. This method can be very efficient because the processes communicate through a common memory area. But there is one important responsibility. The processes must make sure that they do not write to the same location at the same time. Otherwise, data inconsistency may occur. So, shared memory provides faster communication, but proper synchronization is very important. Now look at the diagram shown on this slide. We have process A at the top and process B below it. Between them, we have a region called shared memory. Both processes can access their common region. The kernel is shown below the processes. The important idea is that a process A can place information into the shared memory region. Process B can access the same information. Similarly, process B can place information into the shared memory and process A can read it. So the communication happens through the shared memory region. But remember, both processes must coordinate their access. If process A is modifying some data, process B should not simultaneously modify the same data. Otherwise, we may get incorrect results. This brings us to an important cooperating process problem called the producer-consumer problem. The producer-consumer problem is a very common example used to understand cooperating processes. Here one process is called the producer, the another process is called the consumer. The producer produces information, the consumer consumes that information. A simple example is a compiler. A compiler may produce assembly code. That assembly code is then consumed by the assembler. The assembler in turn produces object modules. These object modules can then be consumed by the loader. Another example is a web server. The web server can act as the producer. It produces information such as HTML files and images. The client web browser acts as the consumer. The browser consumes that information. So we can think of this communication as producer, buffer, consumer. The buffer acts as the temporary storage between the producer and the consumer. Now there is an important problem. The producer and consumer must be synchronized. Why? Suppose the consumer tries to consume an item before the producer has produced it. What will happen? The consumer has nothing to consume. Similarly, suppose the buffer is already full and the producer tries to insert another item. The producer cannot continue until space becomes available. So the synchronization is required. There are two types of buffers. The first is an unbounded buffer. In an unbounded buffer, there is no practical limit on its size. The producer can continue producing items. The consumer may have to wait if there are no new items. The second type is a bounded buffer. Here, the buffer has a fixed size. If the buffer becomes full, the producer must wait. If the buffer becomes empty, the consumer must wait. This is the basic idea behind the bounded buffer producer consumer problem. Now let us look at the simple producer consumer algorithm shown on this slide. First we have the producer. The producer continuously produces an item, then it checks whether the buffer is full. The condition is shown is in plus 1 modulo buffer size equal to out. If this condition is true, the buffer is full. So the producer waits and space becomes available. The producer places the item into buffer of in. Then the value of in is updated. It moves to the next buffer position using the modulo operation. Now let us look at the consumer. If the consumer first checks whether in equal to 0. If this condition is true, the buffer is empty, so the consumer waits. When an item becomes available, the consumer reads the item from buffer of out. Then the value of out is updated. So the basic operation is very simple. The producer puts the item into the buffer, the consumer removes out items from the buffer, and synchronization ensures that the producer does not overwrite valid data and the consumer does not read unavailable data. Now let us move to the second major IPC model, that is message passing. Message passing provides a mechanism through which processes can communicate without sharing the same address space. This is particularly useful in a distributed environment. For example, two communicating processes may even be running on different computers. A simple real-world example is a chat application. One user sends a message, another user receives the message. The basic operations are send of message and receive of message. The message can have a fixed size or a variable size. If two processes, say process P and process Q, want to communicate, they need to establish a communication link. Then they exchange message through send and receive operations. So remember, shared memory uses a common memory region. Message passing uses messages exchanged between processes. Now, when we implement message passing, several questions need to be considered. First, how are communication links established? Second, can one communication link be associated with more than two processes? Third, how many communication links can exist between a pair of communicating processes? Fourth, what is the capacity of communication link? Next, is the size of the message fixed or can the message sizes vary? Finally, is the communication link unidirectional or bidirectional? These are important design and implementation questions. The operating system must provide suitable mechanism to handle these requirements. Communication links can be implemented in different ways. At a physical level, we can have mechanisms based on shared memory, hardware buses, and networks. At the logical level, we can classify communication based on several concepts. First, direct or indirect communication. Second, synchronization or asynchronous communication. Third, automatic or explicit buffering. These concepts determine how processes identify each other, how they exchange messages, whether they wait for each other, and how messages are stored. We'll now discuss these concepts one by one. First, let us discuss direct communication. In direct communication, the sender or receiver is explicitly named. For example, send of P, message means send a message to process P. Similarly, receive Q, message means receive a message from process Q. In indirect communication, the communication link is established automatically. The link is associated with a particular pair of communicating processes. Usually, there is one link between each pair. The link may be unidirectional, but it is usually bidirectional. Now let us see indirect communication. Here messages are sent to and received from a mailbox. A mailbox may also be called a port. Each mailbox has a unique identifier. Processes can communicate only when they share a common mailbox. For example, send a, message means send a message to mailbox A, and receive a, message means receive a message from mailbox A. Unlike direct communication, an indirect communication link can be associated with multiple processes. Let us understand indirect communication with an example. Suppose we have three processes, process 1, process 2 and process 3. All these processes share the same mailbox called a mailbox A. Now suppose P1 sends a message to mailbox A. At the same time, both P2 and P3 are waiting to receive a message from mailbox A. The question is, which process will receive the message? Will both P2 and P3 receive it? No. Only one process will receive the message. The message is removed from the mailbox when it is delivered. Therefore, either P2 or P3 will receive the message. The exact process depends on scheduling by the operating system. The other process continues waiting until another message arrives. So the important point is one message from the shared mailbox is delivered to one waiting receiver, not both. In indirect communication, the operating system must provide mechanisms for managing mailboxes. There are three basic operations. First, a process should be able to create a new mailbox. Second, a processes should be able to send and receive messages through the mailbox. Third, when the mailbox is no longer required, the operating system should allow the mailbox to be deleted. So the operating system plays an important role in managing these communication resources. The mailbox acts as the intermediate location through which processes can exchange messages. This makes indirect communication flexible, especially when more than two processes needs to communicate. Now let us discuss another important classification, that is synchronous and asynchronous communication. Message passing can be either blocking or non-blocking. Blocking communication is considered synchronous. Let us first see blocking send. In a blocking send, the sender is blocked until the message is received. Similarly, in a blocking receive, a receiver is blocked until a message becomes available. So the process waits. Now, in non-blocking communication, the operation does not force the process to wait. A non-blocking send allows the sender to send the message and continue execution. A non-blocking receive may either return a valid message or a null message if no message is available. Different combinations of blocking and non-blocking operations are possible. One important case is when both send and receive are blocking. This is called a Rendovius. So remember, blocking means wait, non-blocking means continue without waiting. Finally, let us discuss buffering. A communication link can have a queue of messages. The messages waiting to be delivered are stored in the queue. There are three main types of buffering. The first is zero capacity. In zero capacity buffering, no messages are queued on a communication link. Therefore, sender must wait until the receiver is ready. This is associated with the Rendo's VS. The second type is bounded capacity. Here, the communication link has a finite capacity. For example, it may hold a maximum of n messages. If the link becomes full, the sender must wait. The third type is unbounded capacity. Here, the queue can grow without a practical fixed limit. Therefore, the sender does not need to wait because of full queue. So, the three types are zero capacity, bounded capacity, and unbounded capacity. This is an important topic for examination questions. So we have come to the end of the today's lecture on inter-process communication. Let us quickly summarize what we have learned first. IPC provides mechanism for process to communicate and cooperate. There are two major IPC models, shared memory and message passing. In shared memory, processes communicate by reading and writing data in a common memory region. We also discussed the producer-consumer problem. We learned about unbounded buffers and bounded buffers and the need for synchronization. Next, we discussed message passing. Processes communicate using send and receive. We then studied direct and indirect communication. In indirect communication, processes communicate through mailboxes. Then we discussed synchronous and asynchronous communication. Blocking operations are synchronous while non-blocking operations are asynchronous. Finally, we discussed buffering. The three types are zero capacity, bounded capacity, and unbounded capacity. These concepts form the foundation for understanding how processes communicate inside an operating system. I hope this lecture has given you a clear understanding of inter-process communication. Please revise the diagram carefully, especially the shared memory model, the producer-consumer model, the direct and indirect communication model, and buffering model. Thank you for watching. Keep learning, keep practicing, and I will see you in the next operating system lectures. Thank you.